Hello and welcome to Disseminate the Computer Science Research Podcast. As usual, I'm your host, Jack Wardby. The podcast is brought to you by Pomtree. Pomtree are the developers behind Raftery, the open source temporal graph analytics engine for Python and Rust. Raftery supports time traveling, multi-layer modeling, and comes out the box with advanced analytics like community evolution, dynamic scoring, and temporal motifs mining. It is blazingly fast, scales to hundreds of millions of edges on your laptop, and connects directly to all your data science tooling, including Pandas, PyG, and LangChain. Go check out what the Pomtree guys are doing at www.raftery.com, where you could dive into their tutorial for the new 0.80 release. Today's a little bit different to the usual episode, which normally focuses around a specific paper. We're actually going to be talking to an individual about their career. And this has been inspired by a blog post called The Most Influential DB Papers, which breaks the most influential work in the DB community across paper, year, and the individuals. And I'm delighted to say that I'm joined by the author of that blog post today, Ryan Marcus. So, Ryan, welcome to the show.
Thanks. Appreciate being here.
Great. So I'll tell you a little bit more about Ryan before I'm sure he tells us his story. But Ryan is an assistant professor at the University of Pennsylvania, which was actually where the first episode of this podcast was filmed. So you should go back and listen to episodes 1 through to 5. They were recorded live in the convention center in Philadelphia. Yeah, no, Ryan said, you can correct me if I'm wrong here, Ryan, but I have your sort of research interest down as primarily being ML for systems, right? So with a focus on databases and clouds. So yeah, very short introduction for you there, but yeah, tell us more about yourself.
Yeah, thanks. I mean, yeah, that's about the extent of it. New faculty at UPenn. I just started this year. My lab is trying to do what we've been calling next generation data systems. So trying to build data systems that can adapt to changes in environments and data layouts, trying to build data systems that can invent new algorithms or approaches to solve problems autonomously, and data systems that are intentional, that go beyond kind of just SQL query in, result out, but have a deeper understanding of user requirements and especially performance. So, it's a young lab. We're still getting started. Haven't done too much yet, but it's an exciting time. It's a great to be started.
Yeah, sounds like a bright future ahead for sure. So let's jump off as a jumping off point. Let's talk about this blog post then. So the most influential database papers. What was the motivation behind you doing it? And yeah, kind of for the listener who hasn't read it, we'll obviously link it in the show notes. Tell us about the blog post.
Yeah, so back in 2016, Mike Stonebraker was giving a talk at the New England Database Day, and if you don't know Mike, he's a very direct guy. He says what he means what he says, and he often puts it in particularly colorful ways. And Mike's talk at this particular New England Database Day was about the hollow core, as he put it, of the database community. He challenged the audience and he said, I challenge any of you PhD students, professors, whoever you are, to name one seminal database paper that has come out after the year 2010. And of course, somebody put their hand up and they said, what about MapReduce? And then Stonebraker went on this whole rant about how much he hates MapReduce and, et cetera, et cetera. But, that sort of sat with me for a long time about, wow, is it really true that there haven't been any like core seminal papers in so long? Is there really this kind of hollow core where no one is working on the essential problems in data management anymore? And as academic in training, I did what all academics do, and I procrastinated it for, 7 or 8 years. But then eventually I decided, okay, let's take a look at this. Let's try to actually take a data-focused approach to try to see, like, okay, what have the most seminal papers be? What have the most influential papers been recently? So I did probably the most databasey possible way of solving this problem. I scraped the citation graph from, Semantic Scholar and a couple of other different places, along with DBLP. Both extremely excellent resources you should check out if you've never seen them before. And I tried to reconstruct this citation graph, in a Jupyter notebook, ran PageRank on it, and then looked at the node weights of each node and sort of asserted like, okay, yeah, that's like an approximation of the impact or the influence of this particular paper. And, the result is this sort of loosely ranked list of kind of like what papers have been the most influential and what authors have created those papers. A lot of data processing and sort of cleaning required to like get all the entity matching correct. I excluded self-citations because if you don't do that, you get all sorts of really weird clusters and loops. There's many instances of Sigmod papers citing, paper A cites paper B and paper B somehow cites paper A. And you're like, how did that happen? But, obviously if someone's submitting a couple papers, then maybe they up their citation counts a little bit. You exclude all those, you factor all that out, and you end up with quite a nice graph. And you can read trends out of that graph quite easily. So if you filter out all the papers past 2010, you see, for example, a ton of work on crowdsourcing, a ton of work on human in the loop data exploration, which to the slightly newer folks in the DB community like me is sort of like, oh yeah, I guess, to me, it's felt like that has always been around, but it was quite new at that time. And if you look at 2015 and onward, you see this big shift towards machine learning for database systems and database systems for machine learning. So, papers like Snorkel and HoloClean, and Andy Pavlov's work on large-scale machine learning models for tuning databases, and Tim Kraska's work on learned index structures. So the conclusion of my experiment, I haven't talked to Mike since writing the blog post, but I do think there have in fact been several major seminal papers since 2010. And it's quite interesting that the data-driven methods that have been predominantly developed by our community were in fact the methods that were able to identify what these influential papers were. Yeah, so that was goal number one with that particular blog post.
Mission accomplished. I mean, that's funny. I'd love to get Mike Stonebreaker's take on it and say, like, we've proved you wrong, Mike. Like, the evidence is here. It shows. Like, yeah.
Yeah, I'll let him know.
Well, I'll email him the link to this podcast saying, Mike, you need to check this out. But that's awesome. Yeah. I mean, it'd be actually, you're just I'm looking at the blog post now on my other screen, and it is really interesting. Kind of, you just sort of like looking back kind of at some of the stuff in the most influential one of all times, I guess, is one by Pat Selinger, right? Which is the access path selection in relational database management. And these other ones are they're so different to what you see in conference proceedings today, right? But yeah, no, that's awesome. And as
absolutely.
Yeah, it's the inspiration for this show and trying to get some of these folks on to come and talk about their work. So I guess with that, let's talk about your story then, Ryan. So very brief introduction at the top of the show, but yeah, tell us more about your journey. How did you get to where you are today? Did you always want to be a database researcher?
Yeah. Like all 4 or 5 year old boys, I grew up with dreams of writing SQL queries and functional dependencies and all. No. So I got into computers at a young age. My dad worked in IT, introduced me to this wonderful programming language called, or programming environment called HyperCard. And I was, hooked from day one, started programming quite a bit. I went to college, to the University of Arizona, decided to do an undergraduate degree there. And while I was there, I interned during several summers at Los Alamos National Lab with their high performance computing team. And this was really the first time that a program that I wrote didn't complete instantly. Like, it was the first time where there was a significant amount of compute, there was a significant amount of data, that the choices that you made really, really mattered. And that was very fascinating to me and very addictive, right? Because you have this program, the goal is to get the program to run faster. And so you do some work, you optimize some Fortran code, you change some MPI routines, or, whatever it is you do, then you run it again and you see 20% improvement. And that's a very both productive and addictive thing to realize. It's like, oh, I can make these performance improvements and I can do this and I can make the program faster. And, all the physicists who wrote the code are very happy with me, and, all that great feedback loop, right, that you get from software development. And everybody that I worked with at Los Alamos National Lab, they all had PhDs. They were all, physicists or computer scientists. And they advised me, they were like, well, if you want to continue your career here, if you want to keep going in this direction, the thing that you should do is you should go and get a PhD. It was sort of the de facto option. In retrospect, that's a really bad reason to get a PhD, just because everyone tells you to, but it's what I did. So, okay, it's applied to a bunch of programs. And I ended up picking a really small program outside of Boston at Brandeis University, because it had a whole bunch of faculty who worked on not just high performance computing problems, but also on data problems. And I continued to collaborate with Los Alamos a little bit, as well as with Brandeis. And the two types of problems that we really found were at the core of these high performance computing challenges was, first, the orchestration of data, and second, the optimization of the routines that access data. So the orchestration of data is like, how are you going to lay out the data that you need to access to? What's your strategy for, in the HPC world, doing stuff like checkpointing, et cetera. And then optimization is, much closer to the traditional database problem of like, okay, now I have all this data. I know logically how I want to construct it back together. I know, the steps of the computation I want to take, but what's my actual plan? When do I move the data to the compute? When do I move the compute to the data? When do I do all these particular things, right? And, Brandeis and Los Alamos were awesome environments to investigate these problems in this kind of scientific computing regime. But as I went through my PhD, I became to appreciate the sort of beauty of relational databases a lot more. High performance computing and scientific code doesn't have the same, the principles and the kind of underlying theorems of relational database systems are, things like functional dependencies, things like the commutativity of the join operator, things like declarative languages like SQL, right? Whereas the first principles of high performance computing in the scientific realm are things like physics and neutron transport and importance problems, but much, much harder problems to grasp and problems that require you to have a national lab level of resources to address. So I started getting really interested in database systems at this point because they provided that same kind of addictive feedback loop, right? Where it's like, okay, I have some workload like TPC-DS, join order benchmark, whatever it is, and I can execute that workload on a database, and then I can make some change to the database. At the highest level, I could create a new index, or at the lowest level, I could implement some kind of new fancy hash drawing routine, right? And again, instant satisfaction. I see that my performance increases. I see that my numbers go down or numbers go up, whichever one you're trying to do, and feels great, right? And that led me down this path at Brandeis where we were trying to do these optimizations for cloud databases. We were trying to figure out how to deal with elasticity, how to deal with, when should you make your cluster bigger? When should you make your cluster smaller? We were dealing with things like scheduling, like if you have a whole bunch of tasks, they have different affinities to different types of hardware. How do you match them up correctly? And we were dealing with problems like tenant placement, like which queries can I run concurrently that don't use the same resources so they won't interfere with each other. And all three of those areas, you can get some really, really big gains by being smarter and smarter and smarter. But what my advisor, Olga, and I realized as we kind of went through these optimization steps over and over and over again was that while very addictive, while very easy to just kind of sit in the chair and make the numbers go down, the solutions that we came up with weren't really generalizing. The thing that made workload A go faster might not have been the things that made workload B go faster. The elasticity strategy for an analytics customer looks totally different than the elasticity structure for a transactional processing customer, et cetera. And so we started to think about, okay, how can we get the computer to play this game for us? How can we use, machine learning techniques or autonomics techniques or whatever you want to call them to sort of play this game of making the number go up or making the number go down for us in a way that automatically tailors its strategy towards the particular customer's requirements. And so this naturally led us to evolutionary algorithms. It naturally led us to a bunch of different machine learning techniques. And then the first thing that really fit, the first thing that was like, oh, this is like the perfect match for the problem was reinforcement learning. So, in reinforcement learning, you abstract away this idea. You say that there's an agent who takes actions inside of some environment and receives some rewards, which is great. And we were very easily able to map our problem in database land on top of that reinforcement learning platform, because we had spent so much time being the agents. We knew exactly what actions to take inside of the environment, and we had identified those reward functions. And it was a really magical connection to find. It was really great. Brandeis was a super small school. So as soon as I kind of figured out like, oh yeah, maybe it's this reinforcement learning thing, I sat in my chair, I turned 90 degrees, and I talked to the person across from me who I knew as a PhD student working on reinforcement learning. And I said, hey, like, what do you think about this? How does this work?
Nice and handy.
Yeah, super, super great. Surround yourself with machine learning experts. Yeah, there's some advice to take away from this. But and I'll kind of paper over, there was a ton of detail, there was a ton of technical work, there was a ton of challenges to solve in getting this to actually work. But essentially, once we found the match between this environment of performance optimization at the orchestration level and reinforcement learning, the rest sort of worked out. There's a lot of science to be done, et cetera. A lot of valuable lessons learned. Maybe I talk about some of them later. But anyway, so that sort of concluded my PhD at this kind of orchestration level of the data, figuring out how to build these, smart clouds, intelligent clouds, automatic scaling, whatever you want to call it. And from there, it seemed like naturally the next place to go was down the stack a little bit into the query optimizer and into more of the sort of lower level algorithms that impacted the performance of the system, right? Because once you get the cluster sizing right and the scheduling right, well, if you want to get more performance gains, now you have to change the thing the database is actually doing, right? So that led me to postdoc at MIT with Tim Kraska and Mohammed Alizadeh, along with the other faculty there, where we started to look at how we could apply reinforcement learning to the query optimization problem. Wrote a bunch of great papers, wrote the NEO paper and the BAO paper, and learned just a whole lot about the actual technical problems you encounter when you try to integrate some of these ML techniques into big systems. It turns out you can't just go up to a production database team and say, hey, we built this crazy reinforcement learning algorithm. We have no guarantees about it. We have no worst case scenarios. We have no upper bounds, nothing like that. Why don't you go ahead and just let this loose on all of your customers? And, they're like, haha, very funny, nice joke. So we had to reformulate a little bit. We had to change a bit from kind of the pie in the sky, craziest reinforcement learning, most advanced ML thing that you could possibly get, which we sort of embedded in our NEO paper. And we had to make the switch towards, okay, what's something that could actually be a little bit more practical, which is what led us to the BAO line of work. And I don't want to go into the technical details of either paper. If we're interested, I can absolutely talk about it later. But yeah. And we did, I think we did a decent job because we were able to take those techniques that we aimed to be more practical. We spun them off into a startup, and that startup got acquired by Amazon. So we spent a little bit of time there. And then, as things settled at Amazon, I left for the faculty position. So yeah, hopefully that story is interesting to someone at least. But yeah, that's the general trace of how things worked. Yeah.
Awesome. No, that's fascinating. It's great that you kind of had a taste of sort of turning something into a startup, because that way you've had the academic experience and then you've had the industry experience as well, and kind of, well, it might get your thoughts later on kind of what you prefer. But I'm guessing by the fact that you came back to academia, I'm kind of guessing which one you prefer to do. But yeah.
Pros and cons,
Yeah. And the other thing I want to say, the Los Alamos, I mean, obviously because of Oppenheimer, that's the same place, right?
Yes, yeah.
Okay, well, that's pretty cool. Just a random observation, but yeah.
Yep. It's a much more developed town now than as pictured in the movies. We have grocery stores and bars and restaurants and all those things.
Oh, wow. How modern. Cool. I guess that leads us up to date then. And so we can talk about your current work then and kind of next gen data systems and what your lab is working on at the moment. What can we look forward to in the next 12 months?
Yeah, absolutely. So the sort of current problems that my lab is working on is very directly motivated by a couple of the lessons that we learned at Amazon. So we actually have a paper coming out at the SIGMOD in Chile about all of these lessons that we learned at Amazon, including some actual data from production workloads. So I'm confident everything I'm about to say is okay. But one of the things that really surprised us compared to coming from academia to industry was our assumptions about workloads. When we were in academia, we assumed that workloads were crazy, unmanageable beasts where every query was super novel. There was very little, there was some, but very little repetition between queries. And, it was mostly analysts sitting down at their keyboards, smashing away at SQL, sending that to the database, getting some results, looking at it, and then trying again. And when we got to Amazon, we were working on the Redshift database at Amazon. We discovered that we were essentially completely wrong. Almost all of the traffic a large portion of the traffic that comes into the database actually is SQL, but it's not written by hand. It's written by BI tools or dashboarding tools or, some automatic tool that's sitting between the analyst and the database, interpreting what the analyst wants into SQL, getting the data from the database, and then displaying that information to the analyst in, a chart or, an analysis or like a t-test or something like that. So that was the first thing we were really wrong about workloads, is that while humans writing SQL is important, and it's a case that databases need to support for a very, very long time, a whole lot of SQL today is automatically generated. The second thing that we were...
Sorry, Ryan, to jump in, what sort of fraction? Because that's a fascinating point, because I kind of myself had that same sort of experience of kind of being the workloads that we work with, TPC, TPCH, and etc. Are they representative of what people are actually doing out there? Is it just some kind of data scientist going wild at a terminal, hacking away? What fraction of it is machine generated at a very high level versus sort of just user generated?
So what I'll point to, it'll get discussed in the SIGMOD paper, but just to make sure I don't say anything I'm not supposed to, there was an analysis by Alex Van Rennen and Thomas Neumann that benchmarked a whole bunch of different clouds analytics databases and took a look at the traffic in the Snowflake system. And their analysis found that over 70% of the queries were machine generated. Amazon numbers are similar ballpark. Yeah. So that was quite surprising.
Yeah, sorry, I interrupted your flow, Ryan. So lesson number 2 line. Yeah.
And things might look different for a graph database or for a transactional database. Although actually transactional databases, I imagine, are even more kind of procedural. Yeah, I don't know, neither here nor there. But yeah, one big assumption that we were making in academia that was certainly untrue is that the main thing a database does is serve queries issued by humans. That is not true. Databases serve queries issued by machines. The interface on the other side of that machine is, there's a user somewhere, obviously, but there could be quite a few layers of indirection before you actually get there. The second big assumption that we had was about workload or query novelty. We assumed that if the user submitted a particular query, then the next query that they submit would be something either like totally unrelated or only slightly related or something like that, but that it would be different, that the user wouldn't be asking like the same question over and over and over again because, you just got the answer to that question. Now you're going to ask a different one. Turns out this is like just radically incorrect. Analytics databases serve dashboards. They serve report generation. They are essentially almost all of the workload is executing the exact same query on slightly different data. Inserts are coming in, data streaming into the database somehow. Some users might do a nightly load, some users stream data in live, et cetera, et cetera. But you have some dashboard, you have some report, you have some process that you care about, some analytics that you want to compute, and you recompute that data periodically, frequently. Obviously, when the data hasn't changed, you just answer the query from the cache. Hopefully every database does that. Maybe some do. If they don't, they certainly should. And then otherwise, you either have some incremental view maintenance, maybe you have some strategy to quickly update that query result and keep it fresh, or maybe you recompute it each time. So this was a huge shock to us. When we were developing our reinforcement learning systems for query optimization, we were assuming that we had this almost adversarial case of like every user query is totally different. What you learned about the query workload yesterday might have nothing to do with the workload tomorrow. And there are some customers, it's a long tail, right? There are some customers where that's true. The exact number will be in that upcoming paper, but there is some, single digit percentage number of customers where almost every query really is unique, but vast majority are these repeated workloads. And this is actually great news for ML for systems people, because it means that you get to try again. It means that if you make the wrong decision the first time that you see a particular query and you get some feedback from it, the next time in the future, you're actually quite likely to see even that exact same query verbatim again later. And you have essentially another opportunity to optimize it. This is an implicit assumption in reinforcement learning algorithms that your past determines your future, but something very exciting that our lab is working on that hopefully we'll be able to release a paper about too, is making this assumption very explicit by actually saying, okay, I'm going to ask the user to tell me, hey, these are the queries that I care about repeating. These are the queries that are running, that I'm going to run every single day. I want you to spend some time optimizing those. And a really interesting opportunity presents itself here when the user tells you, the database owner, I'm going to run this query 100 times a day for at least a year, right? So I know I have at least 365,000 executions of this particular query. Normally, query optimizers, they got to be fast, 100 milliseconds max, preferably much, much less than that. But if you're going to execute a query nearly 500,000 times, it might be acceptable to tell the user, okay, I'm going to spend 5, 10, 15, 20 minutes optimizing this particular query to make sure I really, really, really get it right. Because then when you re-execute this plan over and over and over again, you're going to have the right plan. You're going to make up for that 20 minutes by a long shot. And we're calling this problem learned query super optimization. If I have a whole bunch of offline time, an allocation, not a whole bunch, something on the order of 5 times the query latency, right? So I can try a couple of different plans. How much better can I do in my query optimizer than the sort of one-off type of situation? So that's what our lab's working on kind of near term. Yeah.
A short-term pain for some long-term gain. And I guess there is a tipping point and it depends on the computation, right? I guess potentially kind of how, I don't know, it depends. Like there must be a point where you go, okay, no, we can't take this approach. We have to do it another way because, I don't know, it might need 90% of those iterations to pick the right one. I'm not too sure. So it might take too long, but I'm sure the paper will explain it all.
Yeah. There's two fundamental problems, right? One of them is sometimes you add more search time, but you don't get any better quality, right? And then it's like, well, now I'm just wasting cycles, which in cloud speak means you're wasting dollars, right? Which is not great. So you need to know kind of when your search is done, which is hard to do because there are way too many plans, right? The other issue is you don't know how long your query plan is going to be good for. So like your query plan might be great on the current distribution of the data, but in 6 months, if I'm a startup and now my customer base has quadrupled, hopefully, maybe now the distribution is totally different, right? So you have two problems there. One, can you tell whether or not your query plan has gone stale, whether or not you shouldn't use that same query plan anymore? Can you even notice when it happens? And then if you can notice when it happens, which we think the answer is yes, what can you do about it? How can you adapt that super optimized query plan to changes? So yeah, there's a question of, is the squeeze worth the juice? And then there's a question of, how long does the juice stay good, right?
Please tell me one of those phrases has made it into the title of the paper. I mean, there's so much fun you could have there with that one. That feels like it could be.
We made it into the intro. I don't think they made it into the title.
I always like a good funny title, but awesome stuff. I look forward to those. Sound really, really interesting. And the next sort of section of the podcast, I kind of wanted to. We mentioned it a little bit before when you was telling us your story, but kind of look back, kind of a bit of a retrospective of the papers. And you've mentioned things like BAO and NEO over the course of your career so far. And I guess the first one is, which one are you most proud of in your career? Is it the Best Paper Award?
There's a funny thing about Best Paper Awards, and we were obviously very, very thrilled to get it for the BAO paper. That's an exceptional honor to get in front of the whole community that you've been working with for decades. But we find that the BAO paper got rejected more times than any paper I've ever written. I think it was rejected 3 or 4 times before it got in, and the reason it got rejected so many times is because, on the one hand, you had these traditional query optimizers that had very, very low latency, relatively low complexity in the sense that they were already implemented, but, kind of just okay performance. And then on the other extreme, you had these NEO-like systems, these crazy learned optimizers that use deep learning and all this fancy stuff and got these huge, massive improvements, right? But had all these operational difficulties, all these operational challenges. And with BAO, we were trying to hit the sweet spot. We were trying to say, okay, how can we take advantage of all that infrastructure that exists today, all of the literal, probably a century of human effort concurrently that have been put into these query optimizers, not throw it out entirely, but build on top of it to steer it in a way so that we get some of the gains of those crazy ML systems without the massive operational complexity. And reviewers, a lot of them said, like, okay, you've lost the advantage of the crazy deep learning thing because you're no longer getting as good query performances, and you're also adding this operational burden on top of my traditional optimizer, right? So like, this is not the best of both worlds, it's the worst of both worlds. And it took us a very, very long time to kind of get the story right, get the tech right, to make that really happen. And the reason, the symptom of this, the thing that you can observe as to confirm my story, is that the BAO paper came out, and then 6 months later, our collaboration paper with MSR applying it to their scope system came out. And obviously we didn't publish the BAO paper and then get all that work done in 6 months, right? Like, we were really, really trying to push it forward. So yeah, I am definitely proud of the BAO work, but probably not because it got the Best Paper Award, although I am very thankful for that. I'm mostly proud of it because our whole team, everyone who worked on the BAO paper, was really excited about it and really pushed it through to an extent that I would have never imagined. They put a lot of faith in me and in my ideas. And then not only did they help me execute, but they went off on their own and execute. Pari Negi, who's a just graduated PhD student from MIT, was one of the people on that paper, took it to MSR, applied it to Scope, built it up there, went super well. Christoph Anesser at TUM, who didn't work on the original BAO paper, but was, talking with our team at MIT at the time, took that idea to Meta, implemented it in this thing called AutoSteer, wrote a paper about it. And just seeing, I think the thing that I'm most proud of is seeing other people take up that idea and apply it to, real systems and produce kind of amazing results with it. That was really awesome to see.
I mean, what a validation of your idea, right? That someone else has gone off and had some, actually used it and kind of applied it to kind of different systems and talk about impact as well, right? I mean, I always talk about impacts on the show and ask people about the impact of the work, but I mean, how do you get much more impact than that, right? I mean, that's pretty ticks all the boxes almost, right?
Yeah. Unfortunately, every time someone uses the system in these industrial contexts, my H-index doesn't go up. So I got to convince my tenure committee. But other than that, yes, I do think the gold standard of impact. And this also goes back to what Mike Stonebreaker was saying in his 2016 talk about the hollow middle, is that the real validation for these ideas, we can play around as much as we want at Sigmod and VLDB and CIDR and ICDE, and we can create crazy stuff that maybe will work in 20 years. Like the real validation of the idea is the mission, right? Like we want to make data accessible to everyone. We want to make it cheap and affordable enough so that people who couldn't use data management systems 10 years ago can use them now. And the best validation you can get for that mission is by having it happen, right? By reducing costs, by creating new capabilities that didn't exist before, and by deploying into the real world.
Yeah, awesome. Yeah, that's fantastic. I guess we can maybe talk a little bit about, I have a section here written down, motivation and inspiration, right? So, I mean, obviously there's the blog post that's kind of brought us together today about the most influential database papers. So yeah, kind of what are your favorite papers and which ones have had the biggest impact, you think, on your career over the years?
Yeah, sure. Okay, let me start with a story that will initially sound off topic, but
okay, go for it.
So when I was first kind of getting to know the database community, I noticed a lot of name dropping. I think it's a problem our community has. People will say like, oh yeah, that Jim Gray paper. Oh yeah, to Thomas Neumann's new database system. And like, you're just kind of supposed to know what those things are, right? You're just supposed to like learn at some point, like who Thomas Neumann is and all of these people. And you do very slowly over time, but you kind of like make some stupid mistakes along the way. I once asked, so I was once asking a conference speaker at Sigmod when I was a very new PhD student, and the speaker was talking about the cost of crowdsourcing and how getting more and more humans into the loop kind of added more and more and more to your cost. And I raised my hand and I asked a question, and I was like, oh, well, don't database systems oftentimes actually like account for this? Like for example, the CrowdDB paper, are you familiar with it? And the speaker was Mike Franklin, who was of course the first author of that CrowdDB paper, but I just didn't know who they were or what they were what they were about. So
yeah. I mean, it's a name on the paper at the end of the day, right? You mean not necessarily like there's not a little picture there that says this is what Michael Franklin looks like.
Right, exactly.
There, right? So yeah. I think you can be forgiven for that one, Ryan. Yeah.
So yeah, a little embarrassing, but it's fine. We move on. So other thing that I really wanted to do with this blog post, besides try to answer Stonebreaker's question, was also try to create a tool for people to kind of explore not just the citation graph, but also sort of the more prolific names that are out there in database systems. So, one of the things you can do on that particular blog post is you can click on someone's name, like Pat Sellinger, for example, and you can see a list of all the papers that they wrote kind of sorted by this particular ranking. So if you want to know, who is Sam Madden and what is he famous for? If you click on Sam Madden's name, you'll see kind of like the top particular papers that Sam wrote. And I found, I think, through this process over many years, because I wrote the code a long time ago and didn't get around to actually writing it into a blog post for much longer than that, I found probably my two favorite papers in databases ever through this technique. So the first paper that I found was a Victor Leese paper called How Good Are Query Optimizers Really? This is a classic. I read it at the very start of my work in query optimization. It basically goes through, what are the biggest problems in query optimization? How do cost models and cardinality estimators interact? Why do cardinality estimators constantly underestimate? Is there some simple correction? And it really lays the groundwork. I think anyone who wants to do research in query optimization or who wants to understand query optimization papers should stop whatever they're doing and go read that paper by Victor, because it's really phenomenal. The other paper that I discovered this way was an Andy Pavlo paper called Staring into the Abyss. And the idea behind this paper was evaluating a whole bunch of different concurrency control techniques with an eye towards, future systems that were going to have many, many, many cores. I think they give some estimate in the paper about how many.
Yeah, it's 1,000 cores, right? They use it.
Yes, 1,000 cores.
Right? Yeah.
Which has been achieved, which is a thing. You can buy a node with that many core now, not even on a GPU, right? You can buy an x86 node with that many cores. I mean, and that paper is also extremely insightful. I'm not a OLTP researcher, but this paper shone so much light on the trade-offs and differences between these concurrency control algorithms that I had never thought of before. And they really illustrated the trade-offs and scaling points. So yeah, I think both of those papers I discovered through this sort of data-driven method. And I'm very, very glad that I did, because they're both unbelievably excellent. They're also very famous papers. So, you probably could have discovered them by talking to experts as well. But it's nice that, the two things connect. Yeah.
Yeah, yeah. It's funny what you said earlier on about the sort of like people, how the new Thomas Neumann system or things that I remember before. It was my first SIGMOD, and I was still relatively sort of green. And so it was the Aries paper, and someone, you've not read the Aries paper. And I was like, what do you mean? Was I meant to read it before I came? Like, was this some sort of, are they going to test me when I try and get in? Like, is it going to be an exam? But yeah, no, it's funny, but because I mean, there's that much literature out there, right? Like, it's hard to sort of cover everything. But yeah, no, it's just funny. I had a similar sort of experience with that as well. But yeah, cool. I guess switching it up from papers to people then. So kind of the same question, but what sort of people have had the biggest impact on your career then? And kind of like, if you had some, like, what's the best advice you've had along the way and things like that?
Yeah. So I probably got the best and the worst advice in my career from the same person.
Okay, right.
So my a guy named Larry Cox, who he's retired now, used to work at Los Alamos National Lab. He's a physicist, worked on particle transport stuff and that kind of thing. The worst piece of advice that I got from him was, oh yeah, you got to go get a PhD. It's just the next thing. And now that happened to work out very well for me, but in retrospect, not so great. But probably the most important thing that he taught me is that when somebody asks you a question about your work, or when someone challenges an idea that you have, that is not something that you should defend against. It's not something you should view as adversarial. It's something that you should view as an opportunity for you to understand your problem better and potentially start a collaboration. So, I think it's very common, especially in kind of conference talks, where someone will ask a question that's clearly very pointed. And sometimes the speaker will engage with that question in sort of a debate-like style, right? They'll try to make their points and their counterpoints and prove their original argument. And what Larry Cox taught me is that that's not really the best approach. It's much better to try to identify the weakness that that particular individual is pointing out and try to see, is this a weakness in my technique? Is it a weakness in my storytelling? Like, where is this objection coming from? Where have I failed as a communicator that this person is having this particular bit of confusion? And then if you do notice that it's in your storytelling, can you figure out how to improve it? How can I tell my narrative better? How can I re-rate my introduction? How can I change my slides so that it's more obvious to this person who's clearly smart, but who I haven't been able to communicate the idea to? And if you realize it's a technical issue, then, the best thing to do is to say, ooh, that's a really good point. We hadn't thought of that. That's a great direction for future work. Maybe we should work on it together.
Yeah, and now we have a talk, right? Yeah. And we can figure this out. Yeah.
Yep. Exactly. Yeah. And now you've gone from a semi-adversary to a potential collaborator, right? Big shift. Yeah. But I think the specific advice is good, but the mindset is the most important thing, right? To think about challenges and rejections to your work, not as like judgments on you, but judgments on your work or on your ideas, but instead on judgments on either how you communicated that or as opportunities to improve the technical side of your work. And that sort of thinking was critical, not just for my own kind of like mental health getting through grad school is like a way to think about it, but also as a way to interact with the community and to form productive relationships. So yeah, I think best and worst advice from him, my former boss at Los Alamos National Lab.
That's lovely. That's a really nice piece of advice, and having to detach yourself from the ideas. Like, you're not your ideas, right? They're just not. They're not. I mean, we all get emotional attachment to them, right? Because there's something we've kind of brought into the world and nurtured, and getting up there is daunting, right? So soon to give a presentation, and so as soon as someone sort of questions you, it's so easy to go on the defensive. But you're having that mindset, like you say, leads to good collaboration and just, improves your mental health as well, right? Because if you got upset about every rejection or every negative comment, I mean, you can quickly go insane, right? So, but that's a nice segue actually into the next sort of section, and that's about setbacks. And you mentioned actually that the bow paper getting rejected 3 or 4 times. And how do you, like, obviously you've got this mindset, this probably helps you deal with these setbacks and rejections, but is it always easy to put those principles into practice and kind of deal with the setbacks?
Yeah. I think as a PhD student and a postdoc, and now starting out as faculty, I have sort of a threefold rejection handling technique. So the sort of the first rung of it is exactly that advice that I got from Larry. Like, when your paper gets rejected, it's not because your idea is bad. It's not because you're bad. It's not because you did bad work. It's probably, 90% of the time, it's because of how you presented it. It's because, some part of the story isn't clicking, isn't being communicated to other people. And so the way that I think about it is that like the goal of a paper is to convey intuition to the reader, right? So like you did some work, you spent like a year running some experiments or something like that. You write this 12-page paper. Someone should be able to read that 12-page paper in, 1 to 3 hours. And then they should gain all that experience that you did over the course of a year, right? So you're compressing your year of experience into this nice paper. And that's how science moves forwards, right? That's why I can read a paper and I don't have to spend a year, refiguring out physics or Newtonian gravity or, anything like that, right? So when your paper gets rejected, that's not really saying, hey, your idea is bad. The last year that you spent wasn't useful. What it really means is the way that you've conveyed this to me doesn't make me feel like I skipped a year on the bench, right? It doesn't make me feel like I gained some insight or understanding that wasn't there, which doesn't mean that there isn't something to learn. It means it wasn't conveyed properly, right? So you need to go back to kind of the drawing board and you need to think, okay, what did I really learn? What's the real intuition behind my understanding? And how can I convey that to another smart person? So yeah, that's the first kind of level, which I think is often paraphrased as like, your paper gets rejected, not your idea, kind of, which I think is the right way to go. The second level that I try to think about with rejection is that it's a numbers game. And the more often you submit, the more often you do good work, the more often you are to get rejected, but also the more often you are to get accepted. This is a bit of a dangerous one because it often kind of like if you follow this advice to its logical conclusion, you end up with these like minimum viable papers where you like just try to submit as many things as possible. And you flood the committee and then Mike Stonebreaker says something mean about you at a New England database talk or something like that, right? So for me, it's more like a quality times quantity situation, right? The better you can make your paper, the higher the odds are that it's going to get admitted, but you should parallelize across time, not through time. You should say, okay, I might have to submit this paper many, many, many times, making small, tiny improvements to it each time, but it's going to get better and better and better. And that's much better than, throwing a bunch of things at the wall and seeing what sticks. So suppose, that your paper is so good that any reasonable reviewer who sees it has an 80% chance of accepting it, right? Well, okay, there's 3 reviewers. Say if one of them says reject, the other 2, don't have the energy to argue for you. So, actually your odds are slightly below 50%. So maybe you have to submit 1 or 2 times, right? And, that kind of idea of turning rejection into an opportunity for refinement, I think is the sort of second level. And then the third level is pure cognitive dissonance, is pure just saying like, okay, if a paper gets rejected, that's because maybe the reason that paper got rejected is because the idea is too new, it's too crazy, it's too potentially impactful and awesome. And right. And you kind of have to convince yourself a little bit that for some reason you want that, but the reviewers don't, which is clearly not the case, right? Like clearly the incentives are aligned. But sometimes it helps just kind of at that very, very base mentality of like, oh man, I just got to tweak this story a little bit and they're going to see how amazing and crazy and impactful this idea is going to be. So yeah, I think that's the main way that rejection goes. And now I'm in an interesting situation where I don't just have to deal with it myself, but I have to prepare my PhD students for it. And I have to kind of show them the ropes and hopefully I can even give them a healthier attitude towards rejection than I have, right? Hopefully like things can improve with each generation. And, nobody teaches you how to do that. Nobody teaches you how to teach getting rejected to others. You sort of have to just kind of think about it and make it work. Yeah.
Yeah, there's not a session on that, is there? In like
No.
kind of training ever, it's not like you have to deal with it. But no, I think that's a really nice way to approach it. I like the 3 stages of rejection rather than the 5 stages of grief. We've got the 3 stages. Yep. Maybe I can apply those stages to my Tinder profile and my Tinder activities as well.
Yeah, there you go. Yeah, there are opportunities for improvement. Every swipe in the wrong direction. Yeah.
Cool. So you hit an interesting point there, but obviously you've been a PhD student now you're on the other side of the fence, so to speak, and it's with the kind of the creative process. So they're probably very 2 different experiences depending on kind of where you are in your career, right? So kind of how do you probably today approach idea generation and selecting projects and helping people do that versus when you were kind of a PhD student? Has that process changed over time?
Yeah, absolutely. So, when I was a PhD student, I'd say in like my first 2 years, I thought that being a good PhD student meant that you produced a lot of code that was really complicated and did lots of cool stuff. And that I slowly realized over the next, over the full 5 years that like really what it is about, conveying the intuition behind complex ideas through writing, right? Like that's like the main thing that you're going to be doing. You can have the greatest database system in the world. If you can't explain how it works to another human being, it's useless, right? Like it doesn't matter, right? And so I think as a PhD student, I was very wrongly concerned with paper count, citation count, these sort of bibliometrics of like, oh, how much did I publish? How can I get my, next paper in or whatever? What's the smallest change that I can make to this piece so that I can add another Sigmod paper to my CV or whatever, right? Like, and my advisor pushed back against it, but, I was it's a metric, right? And where there is a metric there, you will optimize for it and make number go up, right? Like that's what we want to do. But, towards the end of my PhD, I started to realize that that's not really how it works, right? That's not really where these things come from. So towards the end of my PhD, I started taking what I'm now thinking about as a technique-oriented approach, basically saying like, okay, what's a cool technique that hasn't been used in database systems, and how can I take that hammer, everything else is a nail, like figure out what to do with it, right? So first it was like, okay, reinforcement learning, let's see what we can do with that. Oh, game theory, let's see what we can do with that. And it's a hit or miss strategy. Like sometimes you find something that works, sometimes you find something that doesn't work, but it's not because of your process, right? It's because you happen to get lucky finding a good match between those two. During my postdoc and after my PhD, I switched to a phase that I'll call was more problem oriented. Was like, how can I identify a pain point, something that isn't working super well right now, something that could be faster, something that could be better, and then how can I build a metric around that thing? And now I'll search my library of techniques that I have developed to try to find the best technique to push that metric in the right direction. And then, this was a much better approach than open your algorithms textbook to a random page and see if that's been implemented in a database yet. But, it's still sort of the problem with the problem driven approach is that you tend to be very incremental, right? You tend to target something pretty small, something that's known about now, something that, exists there. So now I'm trying to switch, and I can't really endorse it yet because I don't know if it's going to work, to what I'm trying to consider an idealized version of a database. Basically, instead of saying, what are the problems that exist now? Instead, I'm trying to imagine, okay, what would I do if I had the perfect database? What new problem would I solve? What new capability would I have? What new businesses could I launch if the database was it just worked, zero query latency, everything 100% perfect, right? And then work backwards from there, right? So identify like, oh, okay, well, if I had the perfect database that worked just 100% of the time, then I'd have analytics for everything. I'd make all of my decisions data-driven, right? There's no cost to it. I can just collect all the data quite simply, et cetera, right? Then like, okay, when I teach a 400-person class, forget the little canvas plot, I'm going to go all out, right? I'm going to build dashboards. I'm going to do everything, right? And then working backwards from there and kind of saying like, okay, how can I create that perfect system, but identify the problems in such a way that lead me to that new application, that lead me to that new capability, to that new thing that I want to do. We'll see if it works. Ask me again in 6 years when happens, and then we'll see. We'll see if that's a good way to think about it or not.
I like it, like working back from the glorious future, right? Like, it's like kind of, yeah, I like that. But with each of these sort of three phases, were you kind of aware that you were taking that approach? Was it like a conscious decision that you were like, okay, now I'm in my problem oriented approach.
My problem era.
Yeah, I'm in my problem area.
So I wasn't aware of it as a PhD student. I wasn't aware of the way that I was picking problems. It was just sort of what I was doing to push the envelope, to have something to talk about in the next meeting, that kind of thing. When I was a postdoc, I kind of realized the error of my ways, but I didn't really know what to do about it yet. And one of the great things about MIT is that there are problems everywhere. Like there are so many people crammed into that data center building that you just kind of walk around the hallway and you listen to what people are saying and you're like, oh, okay. This is an unsolved problem. This is an unsolved problem. And this is an unsolved problem. So there it was just sort of working with what I had, right? Well, okay, I have all these great unanswered questions. Let's answer them. And towards the end of my postdoc, I definitely realized the limitations of that approach. I saw how it could be more incremental rather than revolutionary. And so I guess now as faculty is the first time I'm very explicitly being like, okay, this is the new way that I'm going to identify things to work on. So no, I guess to answer your question quite directly, I didn't know at the time, but I became more and more aware of it as time went on. Yeah.
Nice, cool. Yeah. So the next question is kind of the the kind of the mission of the podcast, actually, and it's bridging the gap, or helping to further bridge the gap between academia and industry. And obviously you've had experience in both camps with the startup. So kind of what is your take on the current interaction between academia and industry, and how can it be improved, basically? What are the problems with it? Kind of what's your take on it, I guess? Yeah.
Oh boy. You know those memes where it's like a 2x2 grid, and like on top it's like what I think I do, what they think I do, what I think I do, what they think I do, and like
Yeah.
so I think academia has a perception of industry as like, you know, these like profit driven like
Crazy capitalist monsters who just
yeah,
care about
like J.K. Rowling goblins, you know, like just like
yeah.
the absolute caricature of like no interest in developing scientific understanding, only caring about the business bottom line, and like never willing to share, you know, any data or like work together at all because they just want to minimize risk and maximize profit, right? And then I think industry has this view of academia as like this, you know, hoity-toity ivory tower, like kind of like, oh wow, you know, spherical cow, kind of like, you know, you're gonna sit and look at a blackboard for a year and you're gonna come up with some theorems that don't really help me like improve my problem at all, right? Like you have no interest in practicality, you have no interest in addressing the problems that actually exist, right? And so it's like, to an academic, the ideal industry partner is like a data repository, right? It's just someone who says like, hey, here's a bunch of workloads, let me know if you find anything cool, right? And to someone in industry, the ideal academic is someone is like an unpaid intern, right? Is someone who they say like, here's my bug report backlog, like let me know like if you want to fix any of them, right? And like obviously the incentives are such that neither group is gonna like perfectly be happy, right? So I think the really, really successful collaborations between academia and industry is when the academic incentives and the industrial incentives are aligned. So, you know, MSR has been the model of this for a very, very long time, where it's like, yeah, okay, you know, we have like the fun house where all the researchers stay and they like do whatever crazy thing they're going to do. And every once in a while, they're expected to surface something that improves a product, right? But there are other successful models as well that don't necessarily exist inside of MSR. One of them that's been very successful for me in collaborations with Meta is trying to identify pain points that are academically interesting, right? So like query optimization is a great example where it's a well-contained problem with a measurable objective outcome. And you can say like, you can de-risk it for the industry side by saying like, hey, look, you know, our PhD students will come intern for you, or like I'll consult for you for a bit. You know, we'll sign all the NDAs. We'll do all that stuff that you need to protect yourself and your data. And we have a quantifiable metric. And, you know, after a semester or 2 semesters or whatever, we'll be able to look at that metric and decide if we like where we're going. And if the answer is yes, then we continue. And if the answer is no, then, you know, we walk away and kind of no hurt feelings, right? So I think the most successful collaborations come when those incentives are aligned. That said, I think there are very big kind of day-to-day differences between how people in industry approach problems and people in academia approach problems. And I think both of them could be improved by some influence from the other.
Yeah.
I definitely think academics need some grounding, need some practical push toward solving problems that are more realistic. You know, the 10,000th paper making TPCDS go 1% faster is fine, and it will get you out the door and you can get your PhD and all that stuff. But like, it's understandable that industry is not particularly interested in this. And I think industrial partners will have more productive collaborations with academics if they can recognize that the problems that those academics are interested in are at the core of their business, right? They do matter. And it just takes a little bit of window dressing and a little bit of persuasion to sort of get the academics kind of aligned with what that particular thing is going to be improved. And sometimes it doesn't work out, right? Sometimes your industry has an organizational structure where it's like, you know, shit flows downstream and it's like, hey, you got to solve these tickets. And then the engineering manager is like, hey, researcher, can you solve this ticket for me? And the researcher is like, I have no idea what this is. And like, you know, you have a mismatch. It's like the wrong person for the wrong job. But I think if you can avoid that, and I think you can get the incentives aligned, you can have productive collaborations.
Yeah, I like the viewpoint of thinking of aligning incentives. It's a very sort of economist way of thinking about things. Cool. Yeah. I guess penultimate question now, Ryan. So this is about current trends and where you think, what things have you seen recently, current and exciting advancements that you've observed that you think kind of like, okay, that's really cool, or yeah, what's your take on current trends?
So the hype cycle in databases, right? It's like first, there's some papers at Sigmod that are totally crazy, far out ideas. This will never work. We're never going to implement it. Niche things, they all get put into that one potpourri section of the conference where everyone gives their talk, and like you kind of hear about them and it's like, fine, right? And then suddenly, like 4 years later, half the conference is whatever those topics are, right? And then 3 or 4 years after that, there's industry adoption and the thing becomes what it is, right? So I think I started out my research journey at the first stage of the ML for Systems bit, where all of the ML for Systems researchers could fit in half a conference room at Sigmod. And it didn't matter if you were doing ML for clouds or if you were doing, ML for neural network training, you were in that same conference section, right? And now we're definitely in the second phase of that. We're definitely into the point where like half of Sigmod, half of VLDB has learned in the title, has instance optimized in the title, has some ML component. And I think the industry adoption is also starting. So I think we're right in between 2 and 3 on that current wave, right? And eventually, so, if I were somebody in industry right now or someone looking to do a startup, I would definitely be looking at those ML techniques. They're starting to be mature. They're starting to be usable. They're starting to be good open source artifacts. In terms of like what's coming down the pipeline, right? Like what's in stage 1, it's hard to identify in stage 1 because a lot of trends die there, right? A lot of things like exist for a while in that stage and they never quite make it to stage 2. But I think the most clear stage 1 thing right now is quantum computing and database systems. Now, I should premise this. I know nothing about quantum computing. I did some physics work at Los Alamos. I vaguely know what a qubit is. I know what spin is. I know what those things are. The quantum computer people talk. I don't understand it. I have a lot to learn there. I have a lot to get going there. The current results are absolutely in that phase where people are like, oh, kind of a weird edge topic, kind of like, we don't really understand what it is. But if I take those researchers at their word, which I think is reasonably good, it has a lot of potential. So maybe that's a trend worth betting on. Maybe it's not. I'm not 100% sure what's here or there with that particular thing. The second topic that I think is in stage 1 that I'm a lot more bullish about is kind of either updatable or out of place learned index structures. So, obviously learned index structures for static data that is, or data that is sorted is well into its second stage by now, but a true kind of replacement for the traditional B-tree structures with all the locking, with all the caching, with all the concurrency access, all of those kind of like fine-tuned packages is finally starting to look like it could maybe be a thing. A couple years ago, I think the first paper that kind of put it out there was the Bourbon paper from Wisconsin that kind of showed like, hey, this learned index structure thing and this LSM tree thing are like kind of highly related. And there's a couple of new interesting works that are coming out that are kind of showing that the relationship between the sorted nature of your data and the compression in your index structure is a lot more negotiable than we originally thought. It's a lot more degrees of freedom than just your data must be fully sorted. So I'm a little more bullish on that one, but if I wish I could give a better interpretation of the quantum stuff, but yeah.
So I have one of my friends in the same lab as me. He did his PhD on quantum computing, and he'd occasionally get up at a seminar to give a talk about it. And I think I got past the title. That was it. After that, I was like, "What? It's so confusing. Sounds amazing." And like he was like, potentially very, very revolutionary. Like it's going to change the game. But yeah, it felt a long way. It felt like kind of very early stage 1, kind of 5 years ago. Yeah, and I think we'll get there eventually, right? But it's a case of when, not if, I think, with it. But yeah. I don't think that my brain's capable of understanding it. I think that's the limit for me. But yeah,
I actually think it's unclear whether or not it'll be in our lifetimes. Like I think the hardware is pretty complicated to produce from a physics point of view. But yeah. If you asked me about large language models in 2015, I probably would have given you a similar answer. So,
Yeah, that's true. You never know, right? Everything. The world moves in mysterious ways, I guess. You never know what's next. If we could predict it, we'd all be a bit richer, right? If I could have...
I'd be in finance, that's for sure. Yeah.
Cool. So I only had the kind of one more question. That was, again, about sort of the future and sort of promising directions for future research. But I think we probably covered it off with the answer there. So
I think so.
I guess we can end things there then, Ryan. Yeah, so thank you so much for talking to me today, Ryan. And I'm sure the listeners will have thoroughly enjoyed it as well. Where can we find you on socials if people want to kind of see what you're tweeting or anything like that? Where can we find you?
Yeah, sure. You can find me on Twitter at Ryan Marcus. It's my name. And you can find me on the good old-fashioned internet at rmarcus.info.
Fantastic. And yeah, if you do enjoy the show, please consider supporting us through Buy Me a Coffee. But and we'll see you all next time for some more awesome computer science research.